Hi, this is Shyamala Gauri, Assistant Professor in CSE Department, Rohini College of Engineering and Technology. Subject code CGS 355, Neural Networks and Deep Learning. Unit 5, Recurrent Neural Networks. The topics covered in this presentation are stochastic encoder and contractive encoder. Stochastic encoder. Stochastic encoders are a class of neural networks designed to model the uncertainty in the encoding process by introducing randomness into the latent representation of the data. They aim to generate a probabilistic distribution over the latent space instead of just a deterministic point. The most common framework that utilizes a stochastic encoder is the variational autoencoder, which introduces a probabilistic approach to autoencoding. Working principle encoder. In a typical autoencoder, the encoder maps the input x to a latent representation z, which is a deterministic vector. However, in a stochastic encoder, instead of outputting a single latent code z, the encoder outputs the parameters of probability distribution. Latent space sampling. Once the mean and variance are produced by the encoder, the latent variable z is sampled from the distribution, introducing randomness into the encoding process. This stochastic sampling allows the autoencoder to capture the uncertainty and variability in the data. Decoder. The decoder then takes the latent representation Z and tries to reconstruct the original input X. Loss function. The training objective of a stochastic encoder typically combines a reconstruction loss and a regularization term that forces the distribution of the latent variables to be close to a known prior distribution. Contractive encoders. Contractive encoders are a type of autoencoder designed to encourage the learned representation to be robust and stable with respect to small changes in the input. This is achieved by adding a regularization term to the loss function that penalizes large changes in the hidden representations relative to small perturbations in the input. The goal of contractive regularization is to make the encoding of the data contract in response to small variations in the input. This helps prevent overfitting and encourages the model to learn more meaningful, stable features. Working principle. Penalty explanation. The penalty term encourages the model to learn representations that are less sensitive to small perturbations in the input. This regularization helps the model learn robust features that are not overly sensitive to small noise or variations in the input data. Training. The training objective in a contractive autoencoder is to minimize the reconstruction error while also minimizing the contractive regularization term. This forces the encoder to learn features that are stable and generalizable. Stochastic versus contractive encoder purpose. Stochastic encoders introduce randomness in the encoding process to model uncertainty and variability in the data. This is especially useful in generative models and when capturing uncertainty. Contractive encoders focus on learning robust table representations by penalizing large changes in the hidden representation with respect to small changes in the input. This helps prevent overfitting and ensures that the features learned are more generalizable. Number two, regularization. In stochastic encoders, regularization is done through KL divergence term, which encourages the latent space to follow a known prior distribution. In contractive encoders, regularization is done through the contractive penalty, which encourages the hidden representations to be insensitive to small perturbations in the input data. Number three, generative versus robust features. Stochastic encoders are well suited for generative tasks like data generation, sampling, and modeling uncertainty. Contractive encoders are better suited for tasks where robustness and generalization to noisy or variable data are important. Thank you.